Okay, so good day everyone. So let's proceed to the next topic, guys, which is the cracking moment. Okay, so cracking moment as shown in the figure, which I will explain later. So this is defined on the previous section. Is calculated by assumption that the effect of the reinforcing steel is neglected due to its relatively small area compared to the concrete. Okay, so definitely, guys, now from the previous examples that we have. Okay, so as you noticed, say this one here. Okay, so this one here. So we have a large area, definitely. Uh, Area of concrete, which is B times H, is way greater than the area of AS. Okay, so mm, so this approximation will result to the calculating the flexural stress on the beam based on its gross area properties. Okay, so the flexural stress F in the concrete at any point with a distance y from the neutral axis will be equal to this equation here. Okay, so this is the general formula, which is F is equal to m times y over ig, wherein m is the bending moment, which is less than or equal to the cracking moment. Okay, so meaning uh, so say for example from the figure, guys, so if this is your beam here, so you have B times H, then if you have this cracking moment here, so at this point, so this is MCR. So anything that is greater than no, anything that is moment, or moment that is greater than MCR, so the beam will start to crack at the tension side, no, as you notice here in the figure. Okay, but this M here, guys, this M are any values of moment. Okay, this is the M that is being mentioned here. The bending moment, which is less than, this is bending moment which is less than or equal to MCR. Okay, so that is the moment that you will be using here in the formula. And also IG is the gross moment of inertia of the concrete section. Okay, so let's proceed. So from this equation, the cracking moment will be obtained by replacing the flexural stress with the modulus of rupture, and any R value, any or any Y with will be the distance from neutral axis to the extreme tension fiber. Okay, so from this formula, that is a B in cross multiplied, guys, F IG over Y. So F here, no, from that formula, M is equal to F IG over Y. So F is being replaced with FR. Okay, so modulus of rupture. Then IG is as is, no, the gross moment of inertia of the section. Then Y, take note of Y, guys. Y is be replaced with YT. Okay, so YT here is the distance from the neutral axis, no, neutral axis to the extreme tension fiber. So if you have rectangular beam, then say this is H, then say this is the neutral axis. Say for example this is H over 2, then H over 2, then this is subject to positive moment. So therefore this is the tension side. Okay, so this is the tension side. So therefore this is your YT here. Okay, so your YT is H over 2. Okay, so take note of the definition of YT. Then MCR is the cracking moment. Okay, So let's proceed to our example 2.1. So a beam section shown has the following properties, which is B 400 mm, H 600 mm, F prime C is 28 MPa. So we are tasked to calculate the flexural stresses in the extreme fiber of the beam shown if it is subjected to a bending moment of 70 kilonewton meter, assuming the section is uncracked. Okay, so also we are tasked to compute the cracking moment. Okay. Okay, so for example, we have example here, example 2.1. Example 2.1. So let me draw the section, guys. So this is our section. We have B is equal to 400 mm and H is 600 mm. Okay, so flexural stress in the extreme fiber of the beam, so meaning these are the FC, no, FC. So as being calculated, so say, so this is your neutral axis. So if we try to recall the stress, now the stress diagram, okay, try to recall the stress diagram of our uncracked. Now take note, guys, the assumption there is uncracked. Then the flexural stress there was this one, right? Now FC, this is for the compression side. Then we also have the this one, say going to that direction. Sorry. Okay, so I think this is also the other side now. This is FC as well for tension. Okay, so take note, this is uncracked, now as being mentioned on the problem. So in order to get this FC here, okay, so this is the requirement, guys, the flexural stress that being mentioned. Okay, so we have moment, given moment, which is equal to 70 kilonewton meter. Okay, then we have that formula, which is a FC is equal to my over Ig. Okay, so just simply recall the formula that you have learned earlier. Okay, so for the moment, this is moment, this is equal to 70 times 10 raised to 6. Okay, this is in Newton mm. I think Newton mm. Okay, I think this is not square, this is not included. Okay, so Newton mm. Then y is 300. Okay, so 300 is half, no? So this is a 300, guys. 300 mm y. So this is 300 mm is for both compression and tension. And then over Ig, which we could compute, this is B, then H cube over 12. Okay, BH cube over 12. So therefore FC is equal to 2.991, I think 917, I think, MPa. Okay, so this will be our answer. So this is FC for both compression and tension. Okay, so that is for the letter A. No, this is for letter A, guys. Then for letter B, so for letter B, we are tasked to determine the cracking moment. Okay, so for the cracking moment B, so cracking moment, we have this formula earlier that MCR is equal to FR times IG over YT. Okay, so we will calculate first FR. So we will be using the 2010, no, NSCP 2010, guys, because that is the latest, which is 0.62 lambda times square root of F prime C, that is 0.62 times 1. So this is normal weight concrete, then times square root of 28. So FR is equal to 3.28 MPa. Okay, so this one here, going back, so we have FCR, which is 3.28, then times IG. Okay, this IG here. Okay, so our IG is equal to 7.2 times 10 raised to 9. Okay, so that is 7.2 times 10 raised to 9, and then over our YT. So this is our YT, guys, no, or this is also the Y bottom, no, because this is the tension side, no, that is the tension side. So this is 300. Okay, so therefore MCR is equal to 778.72 times 10 raised to 6. This is Newton mm, so divided by 1000 squared. Therefore MCR is equal to 78.72 kilonewton meter. This is the cracking moment, and definitely this is greater than the given moment, which is 70 kilonewton meter. So therefore we prove that this is really a beam that is uncracked, a beam that is uncracked. So that is uncracked since that is uncracked because, as we notice here in the okay, so as we notice that if this is your MCR, which is 78.72, then the given moment is 70 kilonewton meter. So definitely it is included here, or say we consider there on the other side 78.72, then the given moment, which is 70 kilonewton meter, is in here first. So therefore there's no cracking, no, in that particular portion there. Okay, and that is for 2.1. Okay, so next, let's proceed to our second problem, which is example 2.2. So a T beam has the following properties, which is the width of the flange, which is equal to 1500 mm, then width of the web 300, then thickness of the flange is 125, then overall height is 800 mm. So if the section is uncracked, calculate the stress in the concrete at the top and bottom fibers under a positive bending moment of 108.5 kilonewton meter. Okay, so expect that we'll be getting a we're getting a cracking moment that is greater than the given moment, due to its condition of uncracked. Okay. Then for letter B, if F prime C is 21 MPa normal weight concrete, what is the maximum uniformly distributed load the beam can carry if it is used as simple beam with 7.3 meters span without exceeding the modulus of rupture of the concrete? Okay. So for letter C, we'll repeat B if the beam is inverted. Okay, so we will know more about that later as we try to uh, calculate it now. Okay, so example 2.2. Okay, example 2.2. So let me draw, guys, the T-beam. So 1500 mm. So this is 125 mm, the thickness of the flange. Then this is 300 mm. Then you have a total depth of 800 mm. Okay, so let us first try to calculate the IG, the IG, guys, of the T-beam, because we will be using that later. Okay, so we try to compute IG. So hopefully you are familiar with this one already from your mathematics and even to your mechanics now on how to get the IG for a T-beam. So for a T-beam, we will first try to locate the neutral axis. Okay, so the location of the neutral axis might be below the flange or within the flange. So we will discover it more later. Okay, so what we're trying to do here is we will try to get the two areas, guys. Say this is one. Okay, then this is for the second. Okay, so or maybe shall I say this is the area of the web and area of the flange. Okay, so our first step is to locate the neutral axis. Okay, using the 80 bar y is equal to a1 y1 plus a2 y2. Okay, and so on. Now if you have other areas to be considered. Okay, for area 1, that is the area of the flange, which is 1500, then times 125, which is equal to 187,500 mm squared. Then you have 82, which is 300, then times 800 minus 125. Okay, so as you notice here, now 300 and 800, guys, then deduct with the thickness of the flange. Okay, then this is 202,500 mm squared. Okay, so for so we are done with A1 and A2 already. So we will be getting the Y1 and Y2, or this is the total area, guys. Total area is equal to 390,000 mm squared. Okay, so for Y1, so Y1 shall I say, our datum will be here, no, at the bottom. Okay, you may also choose the extreme compression fiber, no, or the top portion of your T-beam, no, as your datum. Okay, but y1 will be computed this way, from the datum y1, from the datum to the centroid of your area 1. Then this is y2. Okay, y2 is a distance from the datum to the centroid of the area 2. Okay, so that is 800 minus 125 over 2, and that is equal to 737.5 mm. Okay, then y2 is equal to 800 minus 125 over 2. This is equal to 337.5 mm. Okay, so just try to imagine it here, guys, on the figure. Okay, so 800 then minus half. Now this is half, no, half of hf over 2. Okay, so we will deduct that one. Okay, that is for y1, y2. So therefore we will calculate now the y, bar y. Ito dito for bar y. Okay, so we have 80, right, y bar bottom. So we're getting a y bar bottom here because our datum is with respect to the bottom portion of the T-beam. Okay, so we have 390,000, then times y bottom, which is equal to 187,500, then times y1, which is equal to 737.5, then plus 202,500, then times 337.5. Okay, so therefore our y bottom is equal to 529.81 mm. So therefore our y at the top is 270.19 mm. So just simply deduct the y bottom from the total height, from 800. Okay, so this is our y bottom now. Okay, this is our y bottom, then this portion here is our y top. Okay, so therefore we could calculate now, we could compute IG. Okay, so compute IG, wherein IG is equal to summation of the local I, or the local moment of inertia of the area considered, plus the transfer formula, which is area d squared. Okay, so IG is equal to, so first let us calculate the flange, the flange. So flange 1,500 BH cube, ito guys, BH cube over 12. This is for the flange, then plus the area of the flange 187,500, then D. I think you're familiar with D already, so D guys is from the local centroid of the area to the neutral axis. Okay, so that is D1. Okay, so how about for D, for the web? Okay, again, that is the centroid to the neutral axis dito. Okay, so just simply review your mechanics or mathematics, guys, for this matter. Okay, so we have 270.19, that is the y top, then minus 125 over 2 squared. Okay, so that is for the flange portion, then plus again for the web we have B, which is 300, then H 800 minus 125 cube over 12, then plus area of the web 202,500, then 529.81, that is for the y bottom, then minus 675 over 2 squared. Okay, so again, just simply look at the figure, guys, no, as I mentioned. So you have y bottom. Okay, so you have y bottom here, y bottom, then just simply deduct the half, no, half of the y2. This is, I think this is y2. I know that's not y2, guys, because this portion here is the 675 mm, so divided by 2, so and siya. Okay, so that is for our yeah, I think this is y2. No, this is y2, guys. I think this is y2. Okay, that is y2. So y bottom minus y2. Okay, so this one here. Okay, so therefore we have ig now, ig, which is equal to 2.351 times 10 raised to 10 mm raised to 4. Okay, that is for our ig. Okay, so we're done with ig. So I think we're ready with the computation of our stress in the concrete at the top and bottom extreme fiber. Okay, with a given moment, which is 108.5. Okay, so let us compute first the cracking moment. The cracking moment, MCR is equal to FR IG, then YT. Okay, so FCR again, if we try to calculate FCR, or FR rather, FR is 0.62 times lambda square root of F prime C, which is 0.62 times 1.0 times square root of 21. So FR is 2.84 MPa. Okay, so modulus of rupture, so we have 2.84 then times 2.351 times 10 raised to 10, then over YT. So our YT is the Y bottom. Okay, so take note that YT is equal to our Y bottom, because that is the distance from the neutral axis to the extreme tension fiber. Okay, extreme tension fiber. So we have 529.81. Okay, so to simply divide it with 1000 squared, guys, now for you to get a MCR that is in kilonewton meter. Okay, now this is 126.02. Okay, this is the value of our MCR, which is greater than, okay, wherein MCR is greater than our M, which is 108.5 kilonewton meter. So therefore we have proved that the beam is uncracked. Okay, the beam is uncracked. So this is not the final solution for letter A, since we are tasked to get the the stress at the extreme tension fibers. Okay, so this is for compression. Okay, specifically at the top. Okay, so FC compression is equal to M Y top. Okay, so we're using the Y top here, guys, because we'll be getting the stress at the compression side. Okay, then IG. So M here, we'll not be using the MCR here, but we'll be using the M, which is the lesser value of MCR, which is the given 108. Okay, is 108.5 times 10 raised to 6, then 270.19, then over IG, which is 2.351 times 10 raised to 10. Okay, so therefore our stress at the compression fiber is equal to 1.247 MPa. That is for the compression side. So how about for the tension side, or specifically at the bottom portion of the beam? Okay, so for tension, FC tension is equal to MY bottom, then over IG is equal to 108.5 times 10 raised to 6, then over 529.81, then over 2.351 times 10 raised to 10. Okay, so therefore FC at the tension side is equal to 2.445 MPa. Okay, so this is the result for letter A questions for the stresses at the extreme fibers of the beam. Okay, so I hope this is clear already. Okay, so let's proceed to letter B. Okay, let's proceed to letter B, wherein we are tasked to get, okay, in letter B we are tasked to get the maximum. Okay, so take note, guys, the maximum uniform distributed load that the beam could carry if we have simply supported beam. Okay, max, which is 7.3 meter span, without exceeding the modulus of rupture of the concrete. So meaning without exceeding the modulus of rupture. So meaning this is still uncracked. Okay, this is still uncracked. But the trick here is the trick here is the term maximum. So meaning if we will be getting the maximum uniform load, so therefore we will be using M max as well, and our M max will be equal to MCR, because MCR is the maximum moment that is allowed for us to have a uncracked, no, for us to have a uncracked section or a beam. Okay, that is being illustrated here, guys, right? Okay, so this is the maximum, which is the MCR. Okay, so we will be not, or we will not use the 108.5 kilonewton meter, because that is not the maximum, no. So the maximum moment, the maximum moment without exceeding the modulus of rupture would be the cracking moment. Okay, so I hope that's clear with you. Okay, so going back, so we have simply supported beam here. Then we have uniformly distributed load, which is W max with 7.3 meter. Okay, so I think this is right. We have this one here, M max. Okay, so for M max, I think we are all familiar with this already, that M max for a uniformly distributed load in a simply supported span. So M max is equal to WO L squared over 8, right? Now, so since that is in maximum, so that is W max L squared over 8. Okay, so W max, then L, we have L already, which is 7.3 squared, then over 8, and this should be less than or equal to M max, which I have discussed already, that the N max here for uncrack would be the cracking moment. Okay, it's greater than less than or equal to the cracking moment, guys, no? Cracking moment is the 126.02 kilonewton meter. Okay, so therefore W max should be less than or equal to 18.92 kilonewton meter. Okay, so what's the meaning of this? Now, if your W, say for example, if you will have a W that is 20 kilonewton per meter. Okay, so let me correct this one, guys. So this should be kilonewton. Okay, so this should be kilonewton per meter. Okay, so if you have, say, W that is 20 kilonewton per meter, then your beam will be cracked. Okay, will be cracked already. So if you have W that is 16 kilonewton per meter, then your beam could be considered as uncracked. No? So take note that this is the maximum. Okay? So this is the maximum uniformly distributed load that we could still consider that our beam is uncracked. Okay? So I hope this is clear already. Then lastly, for letter C. So for letter C, we'll try to invert the beam. So therefore, the value here, which is y top will be 529.81. Then y at the bottom would be 270.19. Okay, so therefore we have a different value of MCR here, because take note that MCR is equal to FR times the IG over Y bottom. Okay, this Y bottom. Okay, okay, that is Y bottom. So we have FCR or FR rather earlier, which has the value 2.84. Then IG is 2.351 times 10 raised to 10. Then over Y bottom now would be 270.19 mm. Okay, so again, divide this with 1000 squared in order for you to get an MCR that is in kilonewton meter. So the result is 247.116. Now 116. Okay, for MCR. So therefore, again, the same procedure with what we have done in letter B. So we have W max L squared over 8 should be less than or equal to the MCR, which is 247.116. Okay, so therefore our uniformly distributed load, that is maximum in inverted T, is equal to 37.098 kilonewton per meter. Okay, so per meter. Okay, so meaning the inverted T has the greater allowable what is one greater allowable uniformly distributed load than the T beam. So that is the result now for problem 2.2. Okay, so thank you guys for listening, and keep safe everyone.